All right, so here we are on the last of our introductory chapters. Is this chemistry? No, this isn't chemistry. Some of you are going, why can't we get to chemistry? We can't. Not quite yet, Molly. We're getting close. This is still stuff. Most of this will still be stuff you could very well have learned in middle school. But we need to make sure that all this stuff we're all on the same page on, so that next chapter, we can do chemistry. Okay? Next chapter. So today, last week, we focused on matter. Today, I would like to focus on energy. Why? Because, in a way, matter and energy are one coin. Two different sides. Just like, in a way, chemistry and physics is one coin. One side is matter, chemistry. The other side focuses more on energy, physics. Okay? Also, one side is far more interesting. That's matter, chemistry, and the other side is math. Ugh. All right.
I have a certain fondness for saying that everything is chemicals. Mostly, this is because I'm tired of people complaining about all the chemicals that they're exposed to, when literally everything you have ever been exposed to, including the most organically grown lettuce, is composed entirely of chemicals. But when I say everything is chemicals, I am in fact wrong. There are quite a lot of things that aren't chemicals: sound, heat, laser beams, the existential concept of selfness, rainbows. All of those things are things. And all of those things, and also all other things, are in fact, oh God, this is weird, but it's true, they're all the same thing: energy. Everything is energy.
In a way, we could say that everything is matter. But how can we get away by saying that everything is energy? Today, you will understand. Maybe a little bit better, but you'll understand. All right, first target. I can explain what energy is, the four forms of energy, and we will be using in chemistry, and how they relate to one another. So, why do we study energy? Because if we're going to talk about physical and chemical reactions, and matter can be thought of as a study of physical and chemical reactions, do you not know that every physical and chemical reaction involves some kind of energy change? Yes, it does. So really, to just study physically or chemically what's going on is only part of the story. We need to also understand what's going on with the energy part of the equation. So, what is energy? Energy is the ability to do work. Okay. So what is work? Oh, okay. Work is when you push or pull on an object and it moves. Yep, that's it. So, what if I hire Marc Lenoir to push on this wall all day? So, I hire him for $2 an hour, and he pushes on this wall all day long. Comes home and he's exhausted. Okay? His dad goes, "What's going on? Why are you so tired?" "I worked all day." And his dad gets excited because he thought he was a lazy bum. "Really? So what did you do?" "I pushed a wall." His dad is a doctor. And his dad's already had chemistry and physics, lots of it. So he understands the ramification of Mark pushing an immovable wall. So his dad goes, "Did you move the wall any?" And Mark goes, "No, it's a wall." Then his dad says, "Then you really didn't work any." "No, really, I worked all day long." "No, you didn't." Why didn't he? He didn't move. Here's another illustration. This one you're free to use, okay? Just don't tell your teacher that I told you to do this. So the next time your teacher says, "Hey, take the last 10 minutes of class to work on your homework." Work on your homework. Or actually, no. If she says work on your homework, that's it. You got to work on your homework. Just take the last 10 minutes to work. Just sit there blinking at her. So she'll come around and go, I gave you time to work. Why aren't you working? I am. No, you're not. You're not working on your homework. You didn't tell me to work on the homework. I am working. You see, my eyelids are moving. That is work. Technically, you would be correct. She would have to let it go because she did not stipulate what she wanted you to work on. And you are working by pulling and pushing your eyelids. You see, Ruth is working right now. You're working. Oh, she's not working. Oh, she worked. Here's Noah. Noah is pushing A. Then A comes and hits B. So what two things worked here? Me and A. That's right. Me and A. Some examples of stuff that's working. Car moving, writing, radios, eating, batting a baseball, throwing a basketball. One of these you might sit there going, huh? Radio? How's a radio working? No, this is the radio just on, after the radio button has been pressed. What's going on? Your speaker is a magnet. It's an electromagnet. And as you pump electricity through it, it vibrates. Is it moving? As it vibrates, what's it doing to the air molecules that are against it? Vibrating them. And those air molecules are now moving through space, and they go into your eardrum, and you go, oh, yeah, I can hear the music. Is the radio working? Moving things? Yep. The radio is working.
Let's talk about trebuchets. The trebuchet was a weapon of war, but it is also a feat of ancient engineering, so I remember it for that instead of for all the people it killed. Well, I happen to have a very small one that I built from a kit, because I'm a nerd. This tiny trebuchet contains quite a lot of energy. In fact, more than you might suspect. And because we are humans and we like to understand stuff, we shall put the energy it contains into a bunch of different boxes. Let's start with the least obvious one. It's mass. Since, as Einstein told us, energy and mass are the same thing. Now, we're not going to go into detail there. Instead, we'll just say that the energy is well and locked up and extremely difficult to access because the nuclear energy of the wood is not easy to release. Which is excellent because the nuclear energy of this trebuchet, if released, could destroy the entire building that I'm sitting in. This little war machine also has thermal energy. Anything warmer than absolute zero has thermal energy, even very, very cold things. This basically means that all of the individual atoms and molecules are jiggling imperceptibly. Only at absolute zero would they stop jiggling. If I were to touch it then, my hand would instantly freeze and then fall off of me. Absolute zero is very cold. It also has chemical energy, which is stored in the bonds between the atoms. All of the bonds in the molecules of cellulose and lignin that make up the wood contain energy, and some of them could be broken, releasing that energy, which is what would happen if I lit my trebuchet on fire, which I will not do because it took like 4 hours to put together.
Don't want him to light that thing on fire. Okay, he explained 3 types of energy, but actually there's 7, maybe 8. Electromagnetic, electrostatic, chemical, heat, electrical, magnetic, sound, and the 8th one that I like to talk about, which is kind of debatable whether this one is a form of heat energy, is mechanical energy, or the energy of moving objects. Mechanical energy. What is the relationship between them? They can be constantly being converted from one form to another. Let me go back here, because some of you may not have finished copying those. Let me explain to you how that's happening right now. Okay? I have stored chemical energy. Why? Because I like to store more energy than I use up. Okay? I like to store it right here on my tummy. Okay? I am convinced that there is a famine coming. And while you skinny, skinny people are going to be found strewn on the sides of the road, dead of starvation, I will still be going strong because I have stored energy. Okay, I wish I could have stored it back here, but it doesn't store here. Look, I mean, it's like empty. It's empty. My doctor says I have no butt at all disease. Can't we take some of this? I mean, I'd like to be able to fit into my pants better. Okay, but some guys have no butt at all disease. I am now going to take some chemical energy. I'm going to take some chemical energy that's stored around here on my chest area, and I'm going to burn it through a combustion reaction to produce carbon dioxide and water. But the key thing is energy is now converted from chemical to heat. That heat energy is going to be used by my muscles to allow them to contract and to relax. Some of the muscles are going to be pushing up and squeezing air out of my lungs. Some of the muscles are here in my throat and are going to open and close a little aperture that, as the air escapes, vibrates the air molecules in a certain way. So those vibrating air molecules come out of my mouth, go through space, vibrating other air molecules, until finally they get into your ear and they smack your eardrums. Then your eardrums are connected to other little bones and things, and eventually that mechanical energy is converted into electrical energy that goes pulsing through your brain. And when you hear that kind of, when you see that, when that kind of electrical impulse goes into your brain, you recognize it as words. Amazing. So it started out as chemical. Then it went to heat. Then from heat to mechanical. From mechanical to sound. From sound to mechanical in your eardrum. From mechanical to electrical. And somehow your brain interprets that as words, as information. Amazing, but true. So, there are 4 types that we will focus in on. Chemical, heat, electrostatic, and electromagnetic. Okay, we're going to focus on each one of them here in a second, so you don't have to very quickly write these things down. I'm going to go through all 4. First one is chemical energy. The energy that is trapped within the bonds that hold atoms together is chemical energy. Chemical energy. When these bonds are broken, even when they're reformed, energy is released. Sometimes energy is absorbed. We call it exothermic and endothermic reactions. Methane will react with oxygen, breaking bonds to form carbon dioxide and water and releasing some of the excess energy. The match has more energy to begin with than it does afterwards. So energy is released in the form of heat. And then dynamites have a lot of energy in the chemical bonds. A lot of chemical energy. When dynamite reacts, that chemical energy is converted into heat energy. So chemical energy, the energy that can be found in the bonds that hold everything together. Heat. Well, when those bonds are broken, heat is released. That heat is absorbed by particles, making them move faster. So the more heat you have, the faster you go. Have you noticed I've been able to cool the temperature? It's not as hot in here as it has been. Why? Okay. Why? Because Stefan over there has gas problems, and people have been complaining. Okay? If it's a hot room, then when the gas is released, that gas is moving very fast. The hotter that gas is, the faster it. So Mark is complaining, Ruth is complaining, Esther is complaining, even Max is complaining of the odor. If we cool down the room, then what happens to the speed of the particles? They slow down. That's right. So, we can make hot molecules do work for us. A steam power plant, hot air balloons, gunshots. I love that. Who's ever shot off a gunshot? A shotgun, right? It's like teeny tiny little BBs. Aren't they cute? Little babies. And you're thinking, how can that little baby hurt? I mean, if I was to take one of the little shots and throw them against Molly, it would bounce off her forehead. What's the difference between me taking a shot and bouncing off her forehead and a shotgun doing it? Heat. That's right. Heat. Put a lot more energy behind that teeny tiny little baby, and it can do more damage. Electromagnetic energy is the energy that is absorbed and given off by electrons. Some of this energy is visible, most is not. It travels at the speed of light. Now, let me give you are you in the JV team? Your JV? Did you experience something wondrous on Monday? No. You played a game at 1 o'clock in the heat of the day. Yeah. And your brainiac coaches made you wear cardinal. Yeah. Cardinal, folks. Okay, part of the EM spectrum that is released by the light is infrared. Infrared is absorbed and converted into heat by dark objects. Darker the object, the more infrared it will absorb, Ryan. So your brainiac coaches made Farragut bring their white jerseys that reflect infrared and made you guys wear, I think you even wore your dark pants too. So the failure was complete. In other words, they were hotter on Monday than they should have been. Now, come Sunday, you'll see the Miami Dolphins making the Patriots wear their dark uniforms at their home. Normally, you wear your dark at home and you wear your whites away. Well, they have asked New England to bring their darks, because Sunday at 1 o'clock, Morgan, it's going to be over 95 degrees at kickoff in Miami, and it's going to be sunny. And the Dolphins are going to be covered head to toe in white. Why? Because of the electromagnetic energy. They want to reflect as much electromagnetic energy because they know some of that light, the infrared, is converted into heat, and it makes it more uncomfortable. Electrostatic is the attraction between positive and negative particles. You know this. Getting shocked on a cold, dry day. I used to have a cat. My cat was given to me as a gift. It was my birthday present. Her name was Cammie. I loved that cat. I cleaned that cat's kitty litter. That cat loved my wife. Why are cats like that? They don't love unconditionally. Dogs love unconditionally. That cat loved my wife. My wife did not like that cat. That cat would jump up and would want to rub against my wife's feet. My wife didn't like that. She kicked the cat off the bed. I would go, Cammie, come here, rub on my feet. It wouldn't do that. My wife, it would hop on my wife's lap, wanting my wife to pet her. Okay? She would shoo her away. I would go, come here, get on my lap, I will pet you. No. I fed the cat. I cleaned after the cat. The cat didn't like me. To make matters worse, if the cat got upset, it would poop on my side of the bed, never my wife's. So I'm sorry, I am a human being. I got bitter and resentful. So back then we were living in a carpeted apartment. So during the winter, I would rub on the carpet. And we had the little snack called Pounce, where you would jiggle and she would come running. I don't know where she hid. She was always hiding. She was the most antisocial cat I've ever had. She would come, and I would make sure that I had rubbed my feet real good on the carpeting. And I'd go, here's a snack. And I would zap her nose, and she would freak and run back to whatever hole she came from. And I would laugh and laugh. That was so much fun, because I was using the power of electrostatic energy. Electrostatic energy. Okay, you weren't there. That cat was mean to me. Water rising up a tube. How is that explained by electrostatic? You'll see. You'll understand. How about, how in the world, what is the relationship between Mr. Marino zapping his cat's nose and different substances evaporating? You will see. You're not mature enough to understand. All of these forms can do work. They can push or pull matter a certain distance. The SI unit for energy is going to be the joule. It's named after an English dude by the name of James Joule. The joule is our unit that we will be using. Take out a writing utensil, go to the back of your periodic table, find the SI metric English interconversion chart, and add this one to it. 1 calorie is equal to 4.184 joules. We like calories here in America, but the rest of the world likes joules. Joules. So, if you're concerned about your diet, you're wanting a low joule diet. Now, what is the yes? Really anywhere, but I would put it in the metric English conversion at 7 o'clock. By the way, do you know this? That when you see calorie on the McDonald's menu, it's a big C, but there's little c calorie. A calorie, there are 1,000 calories in a big C calorie. In other words, 1 big C calorie is actually 1 kilocalorie. But they discovered a while ago that if you tell people that the Big Mac is 550 kilocalories of energy, they would go, oh my gosh, no, I can't eat a Big Mac, that's too much. But if you tell them, no, it's actually 550 calories with a big C, and don't tell them that really big C is the same thing as kilocalories, then they'll go, oh, it's only 550. It's not that bad. When in reality, it's 550,000 calories for that Big Mac.
Oh my God.
So beware, marketers. James Joule was a student of John Dalton. His family made beer. You know the whole mirage thing? You know, you're looking down the road, it's a hot, and it looks like, oh, there's a river over there. There's no river over there. He was able to explain that it had to do with light being bent by stuff. He proved that heat was a type of energy that could be used to perform mechanical work. 2 reasons why this picture is not from America. It's a low joule. We would say it's a low calorie. And what is it with the English? Why can't they spell the English language correctly? 4.2. So the first one we looked at was, what is energy? What are the different types of energy? And do they all interconvert? Yes, they all interconvert. Now, we're going to look at something that's going to blow your mind. The law of conservation of energy. And how really that's been violated. Heck, the law of conservation of matter has been violated. So what do we do about it? First of all, what is the law of conservation of energy? For the most part in chemistry, it is obeyed. It basically says that energy cannot be created or destroyed. It only changes forms from one form to another. And on your homework, I'm going to ask you to be able to tell me the different energy types that, and what if you have something like what I told you a few minutes ago about my voice, and that's chemical to mechanical, that kind of stuff. Okay, so that's part of your homework for today. Here's the problem. Back in the early 1900s, they were experimenting around with nuclear energy. And what they were discovering is that matter was being destroyed. Not only that, energy was being created. So we had 2 laws that were laws because laws are never violated, and apparently they were being violated. So, different scientists started trying to explain this. Albert Einstein was the first guy to try to explain it. Basically, he came up with, well, he didn't come up with this equation. Somebody came up with the equation later on, but he came up with the concept. Matter and energy are the same thing. If you're going really, really fast, you're energy. If you're going slow, you're matter. We're the same thing. If you're matter and you start traveling closer and closer and closer to the speed of light, you're becoming more and more like energy. We've got some track stars. Natalie, right? You're a track star. So as you're running down the track, do you realize that I can prove to you that you're becoming more and more like energy? You're becoming more and more like light. You're becoming more light-like the faster you go. I, on the other hand, I like to sit in my chair, in my recliner, because I like to be matter. I enjoy being matter. I've been matter for a very long time, and I intend to stay matter. Therefore, I'm not going to run down anywhere, because if you run down there, you become more like light, and I don't want to become like light. Einstein's theory predicted that matter and energy differed only in the speed. So, in essence, matter is slow energy, and energy is fast matter. This helped us to explain what was going on, because in a nuclear reaction, what is going on is that matter is being converted into energy. And it's actually possible now to convert energy into matter. The laws of conservation of matter and energy became one thing in the 20th century. It is now considered the law of conservation of matter and energy, because they can convert from one to another. Now, science fiction has explored this many, many times. Let me show you a beautiful, beautiful movie that tries to explain this. There she is. This is not the Abrams Star Trek. This is the real Star Trek. And this is the real Enterprise, not that fat cow that Abrams did. Hush. If I was to tell you that the Enterprise was now traveling above the speed of light, then in essence, what just happened?
It turned into energy.
It turned into energy. But the Enterprise doesn't turn into energy. Back 50 years ago, they realized that in order for the Enterprise to travel from one planet to another, which is really, really far away, it was going to have to go really fast. It was going to have to travel faster than the speed of light. So they invented warp space. It goes into warp. Well, how? It does. So what happens in warp space? You travel faster than the speed of light. The creators of Star Trek did not understand one bit of what they were talking about. They just knew that somehow they had to violate E equals mc squared. So what happened is this. There were nerds watching the show. And those nerds became mathematicians and engineers. And it's been 50 years. But folksies, they have mathematically proven that it is possible to warp space. What they believe is happening, they've actually been able. Okay, the nerds who watched this back in the 60s and 70s grew up to become scientists, and they've been able to explain this. What is happening is the Enterprise is warping space around it. Basically, what you saw there was space split open, and the Enterprise actually go into an alternate dimension where E equals mc squared is not valid, where you can go faster than the speed of light. In Star Wars, we call it hyperspace. That's right. So you're in an alternate dimension where you can go faster than the speed of light. When they want to go back into this dimension, then the portal opens and they slip back in to regular space. So there's hyperspace or warp space, and then there's regular space. And folks, modern mathematicians have come up with the math to make it work. Now, we're still many years away from having the engineering skills to make it work, but they've come up with the math. Now, for homework, I'm going to ask you to do a little bit. Now, people like Phoebe will already know this, but I want you to do a little bit of research and find out about the concept of transporters on the Enterprise, on Star Trek. And I'm asking you to explain that in light of the laws of conservation of matter and energy being one thing. That is your homework.